Today we're going to be starting chapter 2, and I just want you to be aware that chapter 2 is a really unique chapter. Most people think about geometry as shapes and formulas and things like that, and this chapter is a lot to do with what they call reasoning and proofs. So in this chapter, you're really going to dive into Euclid's principles of the rules of math, let's say, or the laws of math. So they're going to be kind of talking about, well, why do these angles add up to 90 degrees? Or what makes that true? So in a way, you need to really switch your mind to almost what a lawyer would do. So if you think about if you were a lawyer and you were trying to go to court and you were trying to build a case of, I didn't do it because I was here, or I couldn't have done it because I was at work, or I don't have a car, or these different reasons. And so you're kind of almost laying out like an alibi, like step 1, step 2, step 3. And so that's what you're going to be doing in this chapter. So it's very unique, and I just want you to be aware of that before we dive into chapter 2. So starting off with chapter 2, lesson 1, it's called conditional statements. Now, I am going to go kind of fast here because it's 3 pages, but please know that at any time you can always stop, you can rewind, and also know that there is a hard copy of these notes uploaded in our Google Classroom as well. So first of all, you know what a statement is, okay? A statement can be really like anything, like I'm tall, or if you're tall, then you're smart, just different things like that. A conditional statement is kind of what I just said there, is what we call if-then. So let's say tall people are smart. We know that may not necessarily be true, but we could change that from saying tall people are smart to if you're tall, then you're smart. Really means the same thing. We're just adding the words if then. And so that's what they want you to do in part of today's lesson. Now, they use these goofy symbols, P and Q. So P and Q don't really represent anything other than P is the first part of the statement and Q is the second part of the statement. And you'll see those letters coming up later. But again, it really doesn't matter. P doesn't actually stand for like principles or properties or parallelograms. It's just kind of an arbitrary letter. And so they give you an example here. If it's raining outside, so raining outside would be your P, then I will bring my umbrella is Q. Now, if you notice, I have a tendency to write my Q's in a capital letter. It really doesn't matter if you do lowercase or capital. Again, that's kind of irrelevant. It's just if it's raining, then I bring my umbrella. Okay, so now they want you to practice writing these. Now, chances are, because we're doing a lot of this online, you're probably going to be choosing out of a multiple choice. But I still think it's good for us to practice. So it says, all birds have feathers. So sort of like birds would be our P, feathers would be our Q. So let me rewrite this. Now, if I say, if you're a bird, that kind of sounds funny. So how about if an animal is a bird? Do you notice how I had to insert like an extra word to kind of make it flow a little better? So if an animal is a bird, then it has feathers. So again, we didn't really change the meaning of that statement. We just put it in what's called if-then format. Now, if we look at number 2, this one is practically done for us. It's just kind of reversed. You are in Texas if you live in Houston. So notice the if is coming second. We need to put this first, and we need to put this second. So we would say, if you live in Houston, then you are in Texas. So that would be our conditional. Now what they're going to do from here is they're going to get into kind of like almost relatives and like how can we manipulate the conditional. So the first thing they talk about is the negation. Now really the negation itself is more used in other properties on the next page. But just so you know, the negation is kind of like when we do the opposite. So if you said, I am tall, you would say, I am not tall. Or if you said, I'm not hungry, you would say, I am hungry. So we're just doing the opposite. And they use this goofy little kind of squiggle mark. It kind of is like a little, like kind of cursive, like little wave there. So if you notice down below here, number 3, it says the ball is red. So we just want to simply say the ball is not red. Now, again, I don't know if this is true or false. Maybe it is red. They're not asking me about that. They're just simply asking me to write it, and so that's all I'm going to do. So take a look at number 4. It says the cat is not black. So now the opposite would be to remove this. Over here, I had to insert it. On this one, I'm going to remove it. So I just say the cat is black. Now, you don't always see this. You don't always write these a lot. What you'd use them in is the relatives. So if we move on to page 2, we have 3 relatives: the converse, the inverse, and the contrapositive. Now, the converse is probably the most important. That's probably the one that we use the most in later chapters. So if we think about the conditional is P to Q, so like if P, then Q. So if we think about the conditional like that, the converse just basically switches these. So we would do Q, then P. And if you notice, there's a converse right down here. So you're going to see me give another example here in a second. And remember, I know I'm going kind of fast, but I'm trying to do that so that this video isn't super long. All right, inverse. Inverse is we're going to negate both of them. So we're going to do opposite P to opposite Q. So we're just doing the opposite. The contrapositive is kind of a combination of these two. So we're going to basically switch it and negate it. So we're going to do opposite Q and opposite P. Now, again, you don't see these two that often. They come up from time to time, but for the most part, like when we get to chapters 3 and 4, you see the converse a lot. This is the one that's going to keep resurfacing. So let's go ahead and take this statement. And if you want to pause it here, you can go ahead and try the conditional by yourself. So hopefully you paused it and tried it. Now, if I were to say if a 30-degree angle, it kind of sounds weird. So I think I'm going to reverse this and say if an angle is 30 degrees. Notice I changed it, but yet I didn't like change the degree or the value or the meaning. So if an angle is 30 degrees, then it's acute. And again, I don't think I have to say the word angle again. I could, but it's just kind of repetitive. So here's my conditional. Now I'm going to do the converse. So now to take the converse, I'm going to switch the two parts. So this is going to come first. But if I just say if it's acute, you don't really know what I'm talking about. So how about we say if an angle is acute. So essentially I'm just switching acute and 30. Those are the two pieces I'm switching. If an angle is acute, then it's 30 degrees. Okay, how about the inverse? So the inverse, I'm going to go back to the original, and I'm going to do the opposite. So I'm going to say if an angle is not 30 degrees, then it's not acute. See how I just did the opposite? And then finally is the contrapositive. So if we look at the contrapositive, sometimes I just take the inverse in a way and reverse it, or you can take the converse and add the not. So it's again, it's kind of a combination of the two. So if an angle is not acute, then it's not 30. Now, right now, they just wanted you to practice writing and practice what they are. But when you guys, since you guys are online, are going to be doing your tests through the computer, most of these are going to be multiple choice, where it'll give you a conditional and then it'll say, like, identify what this is, potentially with like a drop-down menu, and you'll have to pick inverse, converse, contrapositive, and then you just choose them, okay? Now, down here, they just want you to see if it's true or false. I mean, this is kind of not a big deal, but sometimes it's kind of fun to look at them just to kind of test your knowledge. If an angle is 30, then it's acute. So hopefully you're answering that and you're like, yes, if you're 30 degrees, you're acute. Okay, if an angle is acute, or sorry, if an angle is 30. If an angle is acute, then it's 30. If you're acute, do you have to be 30? So I'd say no. All right, if an angle's not 30, so I can pick any number I want but 30, then it's not acute. Well, think about that. What if I pick an angle that's like 40? If you're 40, which is not 30, then aren't you acute? So then this would be false. If an angle is not acute, so I have to be greater than 90, then it's not 30. Well, that's true. Because if I'm not acute, then I can't be 30. So that's true. So sometimes they'll just ask you about the true and false, like of statements. Now there is one more kind of relative. So see how they listed the 3 relatives? There is one more. It's on the other page. But if we follow along with the student journal, they kind of squeeze this little example in here. So this is kind of a weird little thing. I think the only reason why they squeeze it in here is it has to do with the true and false like we did above. So let's just quick run through these, but notice that these don't have anything to do with converse, inverse, contrapositive. These are just trying to get you to think about stuff that's true and false. So it's a strange little connection. So if we look at these, they want us to determine if they're true or false, and then they want us to explain. You really only have to explain if you say true. And when you explain, they're trying to get you to come up with some type of property. So like, why does it allow you to say that it's true? If you say it's false, in a way, you can kind of just move on. So let's take a look at these angles. JMF and FMG. Are these supplementary? And so if we were in class, I'd be asking for your feedback, but since I'm alone, I would say, yes, these are true. Yes, these are supplementary. And what would be my reasoning, or what would be my property, would be that these are a linear pair. Now, I really like to use abbreviations. Lots of people in math do. So we usually list this as LPP. And we learned that in chapter 1. That's called the linear pair postulate. So why don't you guys pause the video here and try 8, 9, and 10 on your own. Okay, hopefully you paused it. It says M is the midpoint. And if I look at this, I really can't be sure that these two pieces are equal unless they give me more information. So I'm just going to say false and I move on. JMF and HMG. Are these vertical? I would say true. And my property would really just be the definition of vertical angles. Vertical angles say that they share a common endpoint and they're formed by 2 straight crossing lines. So I would say, yep, these are vertical. And then the next one, line FH and GH, are these perpendicular? Do they form a 90? And I would say no. I mean, first of all, that definitely doesn't look like it. It looks more obtuse or acute. But unless they tell us it's 90, we can't really assume that. Okay, then the last page here is a biconditional. Biconditional is the other relative. So again, I don't know why they didn't just put them all together, but if you look at the way the student journal's written, this is how they have it laid out. So a biconditional is really used in definitions. So let me just give you an example. If you think about a square, okay, sorry, I dropped my highlighter. If you think about a square has 2 parts to its definitions. And again, if I was in class with you, I'd be asking you. And so hopefully you're thinking it's got 4 right angles. But what's the other part? Because if you just say 4 right angles, then you could be a rectangle. So what also makes a square unique? And so you should be saying 4 equal sides. Now, these are the 2 parts that make up a square. But does it really matter which one I said first? Because some of you might have said this one first, but since I'm all alone, I thought of this one first. This is a biconditional. A biconditional basically means it doesn't matter which one we start with, okay? And so if you notice here, sometimes you'll see this goofy little double-edged arrow. And then when you write the conditional, we use the words if and only if. Because it doesn't matter if we have 4 right angles or 4 equal sides when we start. Now, sometimes we also abbreviate if and only if as IFF because math people hate to write. And so any way they can do shortcuts, they will. Okay? And so right here, they're giving you another example. Now, this one's a little longer. They notice how they give you the conditional, and they give you, I told you the most commonly used is the converse. So if they give you the conditional, if two lines intersect to form a right angle, then they are perpendicular lines. Okay, that's true, that makes sense. If two lines are perpendicular, then they form a right angle. Yeah, that's true both ways. So notice what they did was they put it together. So does it matter if you say right angle or perpendicular? Because notice in this one, it says perpendicular and then right angle. So see how they almost like switched them? It doesn't matter which one you put first. So you drop the original if and you drop the then and you put IFF in the middle. Now, typically most people just take the first statement and go right in order and they don't change a single thing other than the if and the then. They don't switch the order, but you can if you want. It's totally up to you. So let's go down and we'll try two examples. Now, number 11 is a little bit shorter than number 12, okay? 12 is very similar to this one. It says if two lines have the same length, then they are congruent, which is true because that's the definition of congruent. Same length, congruent, congruent, same length. That's a good biconditional. So what we do is we drop the if and we drop the then, and then we just kind of rewrite it. So two line segments have the same length if and only if they are congruent. Now, I don't even know if I need to say the word segment over again. I think I've already said it, so I think it's fine. If you want to put it in there again, you could. But again, sometimes it's just nice to drop it because you kind of get tired from writing. All right, number 12, it says, if you can run for president, then you're at least 35 years old. If you're at least 35 years old, then you can run for president. Now, this is actually a false statement. See, this one's true. This is good. This is actually a false statement, and we'll talk about that in a minute. But they want me to rewrite it, so I will, but it doesn't mean that it's good. This is not a definition. This is a definition. So I'm going to drop the if, and I'm going to drop the then, and I'm going to connect them with IFF. So you can run for president if and only if you are at least 35 years old. Now again, they didn't ask me if this was good because it's technically not very good, but I can write it. And so if you look down here, this is where they're talking about a counterexample. So a counterexample is when you're proving something is false. Okay, so let's just, since we're talking about this one, let's say, why is this false? Well, it's false because there's more requirements for presidency than just age. Now, I'm not going to run for president, so I don't know everything, but I do know that there is another requirement that says you have to be born in the United States. And that was like one of the issues that came up when President Obama was running for election, because I believe he was born in Hawaii, and I don't know if he was born before Hawaii was technically a state or something like that. So there was some like little controversy about President Obama that they almost didn't let him run for president. So if I was giving a counterexample, I would say like false. This is not the only requirement. Like you must also be born in U.S. state kind of thing. Like there's more than one requirement, all right? So that kind of leads us right into number 13. And number 13 and 14, they've already given you a biconditional, and they're asking you if it's good. So the thing you got to really watch for is this double-edged arrow. You got to read both directions. So it says a rectangle has sides of 12 and 25. Okay, so if I have a rectangle with sides of 12 and 25, if I do the area, notice it says 300. Sorry, it looks like there's a little bit of a shadow there. Let me see if I can turn the light a little. No, that's not very, oh, that's a little bit better. There we go. Okay, so if I multiply that out, it looks on my computer like there was a little shadow. It's 300. So I would say this is good. So if we go this way, that works out. That's really good. But now let's go the other direction. If you have an area of 300, do you have to be a 12 by 25? And so I would say no. There's quite a few different combinations I could give. So I'm going to say false, but I need to give something that when I multiply it together still gets 300, because I still have to make one part true. So to be a counterexample, you still have to have one piece true. So what if we just said a 10 by 30? I mean, we don't have to get real complicated. Obviously, there's other answers that work. You could say a 1 by 300. You could say a 15 by 20. There's lots of different things I'm sure you could come up with. I'm just trying to think of an easy one. Okay, so this is our last one. So why don't you pause it here and see if you can come up with number 14. Okay, so if you tried number 14, the answer is true. It says a natural number, which a natural number just means it can't be a fraction or decimal or anything like that. So if a natural number is odd, so like if you pick an odd number like 1, or if you pick 3, or if you pick 9, or if you pick 11, if you pick an odd number, when you square it, does it stay odd? So 1 squared, 3 squared, 9 squared, 11 squared. But now, obviously, like, that's not everything. And so if you take your graphing calculator and if you go to the y equals and you type in x squared, if you go to the table, you'll see all the perfect squares. So again, right there, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So you could go through and you could just pick any odd number. You could scroll down super, super far. Like, let me scroll out a little ways here. All right, we're into the 40s. Okay, 43. If I square it, yep, still odd. 45, still odd. 47, still odd. So I know this is true. Going this way, it works. But now go the other way. If you start with an odd, was the original number odd? So again, let's go out a little ways. I'm just going to close my eyes and we'll go out a little ways here and then we'll hit stop. Okay, so, oh, look, I stopped at an odd. Notice if it's odd, it started with odd. Notice this one's even, so I have to skip it. Odd started with odd. This one's even. Odd started with odd. So if I go the other way, it's also true. So because I have both of these that work, then this is a true biconditional. Okay? So that concludes 2.1.